Welcome, everyone. Today, we're going to explore a fundamental truth about data in the real world: knowledge is not static. We are excited to introduce OKH-RAG, which stands for Order-Aware Hypergraph RAG. As you can see from the scattered dots transforming into a clear, connected path, this framework is designed to model higher-order dependencies and map out how complex systems evolve over time. Let's start with the core problem. Right now, most large language models suffer from the illusion of permutation invariance, meaning they treat retrieved facts like a random grab bag of information. But here is the reality: order dictates the outcome. Look at these two timelines. If you get a weather warning, close the port, and then the wind gust hits, your outcome is prepared. But if the wind gust hits, the port closes, and then the warning comes out, that sequence leads to disruption. When outcomes depend on how interactions unfold, standard retrieval fundamentally fails. Sequence matters. To understand where we are, let's look at the evolution of retrieval structures. We started with basic text RAG, which uses unstructured data. Then came graph RAG, linking pairs of data, followed by hypergraph RAG for more complex, multi-way relationships. However, none of these paradigms have sequence awareness, they just select a set of facts. OKH-RAG is the next leap forward. It takes the n-ary structure of a hypergraph and adds sequence awareness, shifting the entire paradigm from just set selection to sequence inference. So, how do we architect this? The OKH-RAG pipeline has three main stages. First, knowledge construction and order learning, where we extract entities from unstructured text and sequential data to build an order-aware knowledge hypergraph. Second, the retrieval phase, which uses a query encoder and a trajectory search module. Finally, generation, where this retrieved trajectory is fed into the LLM. The massive takeaway here is at the bottom: retrieval is no longer a ranking problem, it is a trajectory inference problem. To capture these complex, time-sensitive relationships, we needed a specialized entity typology. We break things down into three categories: persistent objects, like the Port of Houston, which anchor the graph; transient states, which capture specific moments, like a cyclone's category 48 hours before landfall; and temporal anchors, which provide the chronological scaffolding to piece it all together. You might be wondering, how does the system know the correct sequence? We use a learned transition model that infers precedence directly from the data. It looks at document order, consistency in entity overlap, and past retrieval preferences that led to successful reasoning. This means the model captures natural, soft ordering preferences that rigid, hard-coded temporal rules simply cannot express. During retrieval, our trajectory inference is governed by 5 structural dimensions, almost like dials on a mixing board. We tune relevance to the query, order coherence, precedence consistency, entity continuity, and phase coverage to ensure we span distinct reasoning stages. Interestingly, if you were to turn all these order-aware settings down to 0, you would just revert back to standard top-K retrieval. To actually pull the best sequence out of the graph, we use beam search. Instead of just independently scoring isolated facts, our beam search evaluates the sequence. The value of adding a new fact depends on transition probability from the last step, the continuity of the entities, and the diversity of the entire path leading up to it. To validate this, we needed a rigorous testbed, so we used SciPortQA. This dataset contains over 117,000 questions based on nearly 3,000 real-world disruption scenarios across 145 U.S. ports. It tracks everything from storm evolution at T120 hours down to impact predictions at T12 hours. It's the perfect environment because it absolutely requires the LLM to track escalation and downstream consequences. Real-world data is messy. On the left, you see a phase-regular regime like Hurricane Alex's clean, stratified clusters where traditional retrieval might actually do an okay job. But on the right, look at Tropical Storm Arlene. It's an evolution-rich regime with dense, cross-horizon connections and transitionary edges. Standard unordered retrieval completely fails in this chaotic environment, but our unified OKH representation handles both seamlessly. The retrieval mechanism is also highly adaptable to the user's prompt. If you ask a broad question, like what is the expected landfall location, the system prioritizes breadth, tracing a cross-horizon path through time. But if you ask a very specific question like which is the closest weather forecast location, it prioritizes depth, diving deep into a single time horizon to extract the necessary details. The results heavily validate our approach. OKH-RAG consistently outperforms permutation invariant baselines. In our metric, standard text RAG scored 0.287, graph RAG hit 0.414, and hypergraph RAG reached 0.511. But OKH-RAG topped the charts at 0.534. Keep in mind, both hypergraph models use the exact same underlying representation. The entire performance gain for OKH-RAG is driven strictly by treating evidence as an ordered trajectory. We even ran a permutation stress test to isolate exactly how valuable this order is. If we remove phase coverage or precedence from our model, performance drops. But look what happens when we do a shuffle ablation, giving the model the exact same factual content, just in a shuffled order. Performance plummets down to 0.487. The takeaway is undeniable. Effective reasoning requires facts to be both completely retrieved and correctly sequenced. To wrap up, we are fundamentally moving away from set-based retrieval, treating knowledge as a bucket of isolated facts, and stepping into the era of trajectory-based retrieval, where we infer the actual reasoning process. True reasoning over complex systems, whether it's operational logistics, failure analysis, or scientific discovery, requires a framework where the sequence of evidence is explicitly modeled, optimized, and delivered to the LLM completely intact. Thank you.